So let's take a look at an example. A lot of vocabulary here, so try and focus on some of these words and these new definitions that we've gone over. Example 2 says to find the position vector of vector v, which is equal to p sub 1, p sub 2, if p sub 1 is equal to the point negative 3 comma 1, so negative 3 comma 1 is a point because of the parentheses, and p sub 2 is the point 6 comma 3. And we're going to do this step by step. Part A says to first plot the points, p sub 1 and p sub 2, with p sub 1 as the initial point of your vector and p sub 2 as the terminal point. So let me go ahead and do that. I'm starting at the origin. I'm going to move 3 to the left, and I'm going to move 1 up. So that represents p sub 1. And let me just go ahead and write the ordered pair just to remind myself. And then p sub 2 is 6 to the right and up 1, 2, and 3. There it is, p sub 2. And that's the point 6 comma 3. Now this is a vector, so I'm going to connect these two and put an arrow on the terminal side. All right, so I took care of that. And by the way, is this a position vector, what I just found? And the answer is no. I've drawn the vector, but this is not a position vector, and the answer for the reason why it's not is because its initial point is not at 0, 0. From the initial point to the terminal point of the vector, determine the horizontal and the vertical movement. Now, I go on to say that the work to determine the movement should be eventually written as a difference of two numbers. But because we have this nice graph, I think that we can just do some counting. And what I mean by that is, to get from p sub 1 to p sub 2, I can see that I would move 1, 2, 3, 4, 5, 6, 7, 8, 9 to the right. So the first part of my component is 9. And then I would move up, it looks like 2. So the way that I could write vector v as a position vector would be 9 comma 2. In other words, if I were to start at the origin and move to the right 9 and up 2, I would get the same vector that I see drawn in blue here. In other words, the same angle and the same magnitude, but just relocated so that it begins at the origin. Now, as these problems get larger and counting becomes a little bit more difficult, we need something to fall back on. And that's why I suggested that we should be able to write this component form, the 9 comma 2, as the difference of two numbers. In other words, where does this 9 come from? And what I'm going to say is that that 9 has something to do with the first part of each one of these components. And it also has something to do with maybe the difference formula that you've seen in previous sections. So I would get that 9 by taking the 6 and subtracting it from negative 3. So in other words, the second vector, x component, minus the first vector's x component. And then for the 2, I would do the same thing. Start with the 3 and subtract the 1. And if I can keep that in mind, then that will help me for times when I can't simply count. And let me summarize this for you on the next slide. So the results of the previous slide can be summarized as follows. Suppose that v is a vector with the initial point p sub 1 is equal to x comma y. And we're going to call it x sub 1, y sub 1, since we're talking about point sub 1. Not necessarily the origin. And the terminal point p sub 2. If vector v is called vector p sub 1, p sub 2, then vector v is equal to the position vector x sub 2 minus x sub 1, comma y sub 2 minus y sub 1. Now another algebraic way of representing vectors is by using what we call a unit vector. And in a unit vector, we say that it has a magnitude of 1. And our definition is a vector u for which the magnitude is equal to 1 is called a unit vector. Using unit vectors, we can come up with another way of writing vectors. Let vector I be the unit vector whose direction is along the positive x-axis. All right, let me just stop for a second. Vector I is going to be used a lot, and it represents a unit vector, meaning it has a magnitude or a length of 1 whose direction is along the positive x-axis. And let vector j be also a unit vector, meaning it has a length of 1 whose direction is along the, what do you suppose? The positive y-axis. All right, so let's try to keep those two separate. Then we would say that I is equal to 1, 0. Because remember what vector I is. It's a unit vector, meaning it has a length of 1, but it's only going along the positive x-axis. So we can see down in this picture on the bottom right, here is vector I, and it is moving 1 unit to the right, 1 because it's a unit, and that's where it's stopping. It only moves along the positive x-axis. And then of course we've got j, vector j, which is not moving along the x-axis, it's only moving along the y-axis. So in component form we would say that that is 0, 1. Therefore any vector which we can write in the form of components a and b can be rewritten as vector v is equal to a comma v, which is equal to a times the unit vector 1, 0 plus b times 0, 1, and we can call this ai plus bj. In other words, I've simply done a substitution. I've substituted the value for the unit vector of I and the unit vector of j. So this is another way of writing vectors. So we could now rewrite example 2. Instead of writing component form 9 and 2, we would say that this is equal to 9 horizontal unit vectors and 2 vertical unit vectors. So let's look at an example. We're going to use the graph shown to answer the following questions. And in the graph, in red, you see vector u, and in blue, you see labeled vector v. Part A, write vector u and vector v in the form ai plus bj. That is, find the position vector of each. All right, and so what we're really being asked to do here is to find the components. Vector u is already starting at the origin, so it's already positioned as a position vector. And so from the origin, I can see that if I move to the right 2 and up 4 units, that vector u can be written as a movement of 2 units and a movement of 4 units. And to write this as a position vector, we will say 2 unit vectors of I plus 4 unit vectors of j. And vector v, now this is not a position vector, so we have to take a look at where is the initial point and where is the terminal point. And in this case, it's pretty easy to count. If we couldn't count, then we would have to identify those points and then subtract. But it looks to me like I'm moving 2 to the right and 2 down. And so I'm going to say in component form that that is 2, -2, or 2 unit vectors moving horizontal and 2 unit vectors moving vertical. Now, I wrote 2i plus negative 2j. I also could have written 2i minus 2j. Part B says find the sum of u plus v. Now, finding the sum means not only to express it, but also to find it in the picture. And the way that vector u and v are connected, they are connected by the terminal point of vector u and the initial point of vector v, and therefore they represent a sum. So the vector that connects the initial point of vector u to the terminal point of vector v represents the sum. Let me go ahead and mark that on the picture. This vector in black would be vector u plus vector v. So the sum is going to be whatever I count as from the initial point to the terminal point. So I'm going 4 to the right and I'm going 2 up. Now I had the picture, so it was easy again for me to do that, but also note that I could have just from what I represented on part A, 2 comma 4 and 2 negative 2, if I took 2 plus 2, that would have given me 4, and if I took 4 plus negative 2, that would get me 2. So that's the other way that I could have done that. Now I'm going to write this as a position vector, writing 4i plus 2j. Now, to find u minus j, I could sketch it out to find it, but I think what I'll do first off in this case is I will actually use or make use of my components. So vector u was 2 comma 4, and I'm going to subtract from that vector v, which is 2 negative 2. And if I do that subtraction, let's see, 2 minus 2 is 0, and be careful here, we have 4 minus a negative 2, and so that puts me at 6. Now, where is 6? It looks like starting at the origin, if I go nowhere on the x-axis and I go up 6 units, it actually takes me off my graph. I would have to extend, right? I would have to extend this graph up above to maybe 5 and 6. So this would end up being, let me put it in green, vector u minus v would be this vertical vector pointing straight up. So let me label that. In green, I have vector u minus vector v. Now remember how we talked about how you actually physically show the vector on a graph. To show u minus v, I have vector u, and then minus v would be the same thing as adding the opposite direction of v. So the vector that we see for v in blue, if I were to reverse that direction, I think that you can see, let me just draw that in, that sure enough would put me in the right position. So going one way is vector v, going the other way is the opposite, and so that checks. Part D says to find 2u minus 3v, and I'm going to stop sketching these on the graph, but you should do this on your own just to make sure that you agree with the answers that we get here. So let me see here. I'm going to say that this is 2 times vector u. Vector u is 2, 4, and then minus 3 times vector v, which is 2, negative 2. And so I'm going to get 4, comma 8, and then let me call this, let me multiply this through. So I'm going to call that, I'm debating on whether I want to change this to, I think I will, I'll change this to plus a negative. So plus, and I'm going to call this negative 6, and it looks like positive 6. And then when I add those pieces of the components, 4 plus negative 6 gets me negative 2, and 8 plus 6 gets me 14. So it's good that I didn't try to graph this one because I think that I would be off of the graph. In fact, it looks like I would be in quadrant 3. And as a position vector with i's and j's, this would become negative 2i plus 14j. So that's just another way of writing it, where the I and j really draw your attention to the idea of the fact that we're dealing with unit vectors. So 2 horizontal unit vectors and 14 vertical unit vectors. And then finally, the last one, it says find. And do you remember what those symbols are? They're 2 vertical symbols, almost looks like a double absolute value, but that represents magnitude. In other words, I want to know what is the length of the sum vector, and we indicated that in black. That was one of the first things that we did. We now want to find out what is the length of that vector. We know how to get to that vector. We start at the origin and we move 4 to the right. We move 4 to the right. And we move 2 up, and that is coming from part B. Now you'll notice that one of the reasons I sketched that out, moving 4 to the right and up 2, was because I wanted you to see that what we formed was a right triangle. So anytime you're being asked to find the magnitude of something that's a diagonal, by knowing the components, you are set up perfectly to calculate using probably the Pythagorean theorem. So I'm going to say that the magnitude of this sum, I'm going to just remind you that this is the length of the sum of these 2 vectors, and that's going to equal the square root of 4 squared plus 2 squared, which is 16 plus 4, or the square root of 20. And you could put that into your calculator if you want. This is also equal to 4 times 5. So if you were asked for an exact answer, this would be 2 root 5. And I'll leave the approximation up to you. So in general, let's define some things that we've talked about. Let V equal AI plus BJ, and that's equal to the components A and B. And we're going to call that A sub 1 and B sub 1, because in vector W we see A and B again, so we're going to call those A sub 2 and B sub 2. So vector V and W we've written in component form. Let those be 2 vectors, and let alpha be a scalar. Describe in words the following. So I'm going to go ahead and use symbols as my language. I'm going to say that vector V plus vector W would be equal to taking the components of A sub 1 and A sub 2, and it would be that many horizontal unit vectors plus B sub 1 plus B sub 2, and that many vertical unit vectors. Or written in components, I could say the sum of A sub 1 and A sub 2 and the sum of B sub 1 and B sub 2. Now for subtraction, it's exactly the same thing. If you want to write it all back out again, you can. I'm just going to say there's a minus here and a minus here and a minus here and a minus here. So everything is the same as the first line. It'd probably be faster if I just rewrote it. I think it would have been. All right, and then the third line, a scalar times a vector. What do we do with that? Well, we multiply. So I would take whatever that scalar is, and I would multiply it by the parts or the components of the vector. So I've got my A sub 1, and I've got my B sub 1. Now we're not talking about vector W on this one, we're just saying some scalar multiple of vector V. And then of course in component form I could just write out the parts. So whatever that multiplication ends up being. So this is just formalizing what we did on the last couple of slides. And then finally, what is the magnitude of a vector? In the very last one that we did, we saw that we made use of the Pythagorean theorem. Now, in case I confused you by putting the square root in there, let me just remind you of why I did that. If I were to say to you, use the Pythagorean theorem, you might say, okay, well, c squared is equal to a squared plus b squared. But normally what I'm interested in is not c squared, I'm interested in c. So I know that what ends up happening is I have to take the square root. So I'm just going right to that square root part. In other words, I don't want to know what the magnitude of the vector squared is. I just want to know what the magnitude is. So I'm going to say that this is equal to the square root of the horizontal component squared plus the vertical component also squared. Now recall that a vector u for which the magnitude of that vector is equal to 1 is called a unit vector. And just like a unit price at the grocery store can be found by taking the price of an item and dividing it by the number of units it contains, a unit vector can be done the same way. It can be found by taking the vector and dividing it by its magnitude. So here's the formal definition. Unit vector in the direction of vector v theorem. For any non-zero vector v, the vector u is equal to vector v divided by the magnitude of that vector. And that's what a unit vector would look like. Now this unit vector is going to have the same direction as vector v. A variation of this would be if I were to take this little definition and just move some things around. In other words, try to get vector v by itself. I'd multiply both sides by the magnitude. So I would say that vector v can be rewritten as vector u times the magnitude of vector v. All right? So keep in mind, on a lot of these problems, a vector might have a magnitude of, say, 7. What we would be doing is trying to find out something about the unit vector. A vector with a magnitude of 7 is not a unit vector. A unit vector has to be something that equals 1. So let me show you what that's going to look like. All right, so I think this example 4 will help make sense out of the unit vector. It says find a unit vector in the same direction as the vector 12i minus 5j. All right, so if you go back to the previous slide, what did I tell you you needed to do in order to find the unit vector? So I think what I said was that the unit vector is equal to the vector that I have divided by the magnitude of that vector. So the vector that I have is 12i minus 5j. And what I want to divide that by is the length of that vector. Now I want you to think about this for a second. Let me just do a quick graph. Now you don't have to do the graph because you also have on the previous slide how to find the magnitude of this vector. Do you remember how to do that? You do that by a variation of the Pythagorean theorem, but let's make sure you understand why. If I wanted to locate where is 12i minus 5j, that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 units on the horizontal axis, and then 1, 2, 3, 4, 5 units on the vertical axis. So vector v is in the fourth, there it is, somewhere about right there. It's in the fourth quadrant. And what's the length of that vector? Well, the length of that vector is simply whatever the hypotenuse is. What's the measure of that hypotenuse? Well, in order to answer that question, I know what each one of those legs is. So all I have to do is use the Pythagorean theorem. So I'm going to say that the magnitude is the square root of 12 squared plus negative 5 squared. And so I get 12i minus 5j. And let's see, 12 squared is 144. Negative 5 squared is 25. If you add those up and you take the square root, I think that's a nice number. So it comes out as 13. Now I'm going to do one last thing here, and let's remember some fraction work. Anything divided by a single digit denominator, another way of writing that is distributing that 13 to each one of those pieces. So I could say that 12/13 I minus 5/13 j. That is a unit vector that is in the same direction as vector v. Okay, so let's see if we can make sense out of this. This is a unit vector. So in other words, if I take that unit vector, now just imagine going 12/13 on the horizontal axis and then down 5/13 on the vertical axis. That's going to get you maybe right here. And then you're going to do another one, and you're going to do another one, and you're going to do another one, etc., etc., etc. Each one of those pieces has a magnitude of 1. And when you put them all together, you end up with the whole vector that had a magnitude or length of 13. All right, I hope that that helps make some sense. And let me just put a vector mark over my eye. All right, let's take a look at another example. In many applications, vectors are described in terms of magnitude and direction rather than in terms of components. If given magnitude and direction, how can a vector be expressed? So let's look at this example. A ball is thrown with an initial speed of 90 miles per hour. Well, this is what we're going to call the magnitude of the ball. We saw this in some previous sections where we knew things, we were going maybe 2 miles per hour, and we labeled that segment by what the distance was. When the ball is released, the angle it makes with the horizontal is 30 degrees. That 30 degrees helps give me the direction. All right, so I think in the picture that makes some sense. You can see the 30-degree angle. 30 degrees is always from the positive x-axis, and so and because it's positive, I'm moving counterclockwise, and then I have a length of 90. All right, let's keep this problem going. Here's what we just did. We said that the speed of 90 miles per hour is the magnitude, and we said that the 30 degrees is the direction. All right, there's a little bit more to this problem. To find the terminal point of the vector, that's where the arrow's at on the vector, use what you know about trigonometry to find the x-coordinate and the y-coordinate. In other words, what is that ordered pair? So you might have to remember back to what we've done in some other sections, but I think that with a little bit of thought, especially with the work that we did in polar coordinates, that you remember that we said that x is equal to r times the cosine of theta. And if that's true, then if you imagine this vector being part of a circle, which we've seen so many times, then 90 all of a sudden becomes the radius, and of course theta is 30 degrees. So what is 90 times the cosine of 30 degrees? Well, 90 times the cosine of 30 degrees, that's going to be what, √3/2? And if I simplify that, I get that the x-coordinate is 45√2. And similarly, y is going to be r sine of theta, and so that's 90 times the sine of 30 degrees. If cosine of 30 degrees is √3/2, then the sine of 30 degrees has to be 1/2, and so this one comes out very clean. So the y-coordinate is 45. Okay, so this ordered pair up here is 45√2, comma 45. Now, that's me being in degrees. Since this vector is a position vector, in other words, its initial point is at the origin, then in simplified form, we could say, and I'm going to clear where I wrote over this for just a minute. All right, we could say that 90 times the cosine of 30 degrees I plus sine of 30 degrees J is equal to 45 root 3, that's my x value, and that's with an I on it, I'm writing it as a position vector, plus 45j. Now, of the initial speed, how much of that speed was in the horizontal direction? Well, the nice thing about writing things in component form is that the I and the j give you those answers. The horizontal direction is going to be 45 root 3. And if I put that into my calculator, I get approximately 77.94 miles per hour. Of the initial speed, how much is in the vertical direction? Well, that's my 45. I don't have to do any estimating at all. That's going to be 45 miles per hour. So the ball being thrown at an initial speed of 90 miles per hour is coming from a horizontal and a vertical miles per hour.